So in this video, I'm going to introduce gases. And so just a couple of characteristics of gases that you should have covered in first year chemistry, or just kind of common sense as well. It's the fact that gases, they expand to fill the volume of a container. That's one characteristic. Another one is that they're highly compressible because there's a ton of space in between gas molecules. And since they're so spread apart, they actually act independently of each other. So they're not attracted to each other, and instead they kind of coexist. And we'll look at how that influences our mathematics a little bit later on when we're working with gas laws. Really quickly, to talk about pressure, pressure is the force that's exerted on a given area. So for example, if I'm stepped on by someone with wedge shoes versus stilettos, the amount of pressure my foot experiences, the force is the same, but the amount of pressure is much larger for the stiletto heel, and therefore it hurts a lot more because the area over which the force is exerted is much smaller. So that's why getting stepped on with stiletto heels hurts so badly. And the last thing to talk about is atmospheric pressure. Now, atmospheric pressure is the force exerted by the Earth's atmosphere. So right now, the atmosphere is actually pushing down on us. The gases in the atmosphere are pushing down on us, and we're experiencing that atmospheric pressure. Now, the barometer is one tool that's used to measure atmospheric pressure, and what it is, it consists of a tube that's filled with mercury, and the atmospheric pressure pushes down on that open bath of mercury that you see right there, which would then cause the mercury in the tube to rise up the higher the atmospheric pressure. And so one unit, I'm going to talk about units of pressure in just 1 second, but 1 unit of pressure is a millimeter of mercury, and the standard for that is 760 millimeters of mercury, because when you're at normal standard pressure, the amount of atmospheric pressure causes the mercury to rise up 760 millimeters of mercury. So one of the first things that you need to learn as far as gases are concerned is the units for pressure. Now, the units for pressure include millimeters of mercury, atmospheres, and then also kilopascals. So the relationship is that there are 760 millimeters of mercury in 1 atmosphere and in 101.3 kilopascals. So let's work on converting from millimeters of mercury into atmospheres. So I have 1,277 millimeters of mercury. That's my given. So I'm going to get out of millimeters of mercury by putting that unit on bottom. And then I'm going to get into atmospheres by putting that up top. Now all I have to do is put the relationship. So for every 1 atmosphere, there are 760 millimeters of mercury. And so I'm going to take 1,277, divide by 760, and what I get, I want 4 sig figs, so I get 1.680 atmospheres. Okay, so I've converted from 1 unit of pressure, millimeters of mercury, into another unit of pressure, atmospheres. We're now going to talk about the ideal gas equation. So the ideal gas law is PV. The equation is PV equals nRT. P being pressure, V being volume, N being number of moles, and T being temperature. Now R is your gas law constant, which will be given to you, and it's 0.0821 liter, atmosphere, Kelvin, mole. And so the reason why these units are important, the liters tell you that your volume must be in liters. The units for volume must be liters. Your pressure must be in atmospheres. Your temperature must be Kelvin, and then moles must be moles. So in this problem, I'm given volume, I'm given pressure, I'm given temperature, and I'm asked to solve for the number of moles of oxygen. And so I'm going to be using the ideal gas law, so PV equals nRT. Okay. Remember, your R value, your constant, is 0.0821, and the units are liters times atmospheres over Kelvin times moles. Okay? So the pressure must be in atmospheres. So I have 2.3 atmospheres. Notice my volume must be in liters. So right now I have it in centimeters cubed, which is equivalent to milliliters. So I've got to divide that by 1,000 to get it into liters. So I have 0.0026 liters. And I'm going to set that equal to, well, I'm solving
for my number of moles, so N, times my R, which I have, which is given to me, so 0.0821, and then times my temperature. So my temperature right now is in Celsius. I need to convert that into Kelvin. And when I do that, I get 299 Kelvin. Okay? And so when I solve for my N, I multiply 2.3 by 0.0026, divide that by 0.0821, divide that by 299, and what I end up with my answer, having 2 sig figs, I get 2.4 times 10 to the negative 4th moles. Okay, so that's the first part of this problem. The next part of this problem asks me how many grams of oxygen is this? Well, I know how many moles I have. I have 2.4 times 10 to the negative 4th moles. And so I need to convert that into grams. So I'm going to put the moles on bottom, grams up top. This is molar mass. So since I have O2, the molar mass of O2 is going to be about 32 for every 1 mole. And so when you multiply this, what you should end up getting for the mass is 0.0078 grams. So there's my mass. I'm almost done. I have one last question, and it asks, what's the density? Remember, density equals mass divided by volume. So here I know my mass. It's 0.0078 grams. And I'm going to divide that by the volume, and the volume I was given at the beginning of this problem was 2.6 centimeters cubed. And I'm just going to keep it like that. I don't need it in liters for this part. Okay? And so when I do that division, what I end up getting is 0.0030 for 2 sig figs, and it's grams per centimeter cubed.
So in this lesson, we're going to be talking about gas mixtures and partial pressures. So the really cool thing about gases is encompassed in Dalton's law of partial pressures. Specifically, if you have a bunch of gases, you can actually take all of their partial pressures and sum them together to find the total pressure of that gas sample. So the formula for this is P total, the total pressure, equals the sum of all of the partial pressures of the gases that exist in the sample. Another way of determining this is to use mole fractions in determining partial pressures. So here's the equation right here. The partial pressure of one gas equals the mole fraction of that gas, specifically the number of moles of that one gas, divided by the total number of moles of the gas, times the total pressure. And it's actually quite easy to determine the total number of moles of a gas. You simply add up the moles. So gases work really nicely because you can simply add their pressures or add their number of moles together.
So for this problem, there are 2 different gases that are given to you, and it's asking for the partial pressure of each gas and then the total pressure. Now there are 2 different ways of completing this problem. I'm going to do it one way. The other way you could do it, you're going to be using the ideal gas law no matter what. And so what you could do is you could solve for the partial pressure of each first by simply taking the 2 gases, converting each of these into moles, and then solving for P. And then you just add them together to get the total pressure. That's one option. I actually like the other option a little bit better simply because it shows just how versatile gases are with respect to comparing them and combining them together. And so what I'm going to do here, just like what you would do for the previous way of doing the problem, I'm going to take the mass of oxygen and I'm going to first convert that into moles because I need to know the number of moles. Okay, so the molar mass of O2 is 32. And so what I end up getting for this is 0.1875 moles. Okay. And so yeah, this would round to 0.19, but I'm not going to round until the very end. And then I'm going to have 9.0 grams, and this is of methane, and the molar mass of methane is about 16.05 grams. And so the number of moles here would be 0.5607 moles. Okay, so if you want to, you can just take each of these, plug them into PV equals nRT, your ideal gas law equation, and then calculate the pressure for each of them. What I'm going to do instead, just to show you how versatile gases are, what I can actually do with these 2 numbers of moles, I can just add them together. And so if I add them together, the total number of moles would be 0.7 0.7482 moles. And so what I'm going to do right now, I'm going to plug that into my ideal gas equation to solve for pressure. So pressure times my volume, which is 15.0 liters, equals my total number of moles, which is 0.7482, times my R, which is 0.0821, times my temperature in Kelvin, which is 273. And so my total pressure, my P total, is going to be 1.12 atmospheres. Okay? And just to use the concept that I introduced just a second ago, I'm actually going to take this total pressure and I'm going to find each individual partial pressure by using the mole fraction. So if I have the pressure of O2, its mole fraction is going to be the number of moles of just oxygen, which is 0.1875, divided by the total number of moles, which is 0.7482. So the mole fraction times the total pressure, which is 1.12. And so what I get for the partial pressure of oxygen is 0.281 atmospheres. For the partial pressure of methane, I'm going to do the same thing, but use its mole fraction, which is going to be 0.5607 divided by the total number of moles, which is the same, times the total pressure, 1.12. And what I end up getting for the partial pressure of CH4 is 0.839 atmospheres. Okay? Now, if I'm going to be rounding properly, all of these values up here should have been just two significant figures, and so as a result, I should take these answers, and instead of 0.281, it should be 0.28 atmospheres, because I waited to round until the very end, and 0.84 atmospheres. Okay? Notice if I add these two together, I get my total pressure. Now, if you did it the other way, where you just took each of these moles and plugged them in and got the individual pressures and then added them together, it still will work.